Bismillahir Rahmanir Rahim. Uh, welcome all. Welcome all for today's session. Today we have Dr. Nilay Kant. He'll be presenting us on a topic, orbital stabilization of underactuated robotic systems. To talk about Dr. Nilay, he has received his bachelor's in mechanical engineering from one of the elite institutes of India, IIT Delhi, in 2015. And further, he pursued his PhD in mechanical engineering at Michigan State. And he was also a visiting researcher at NASA Jet Propulsion Lab in California. And after getting his doctoral degree, he worked as a senior mechatronics and control engineer at Nexteer Automotive Corporation in Michigan. And as of now, he's working as a senior controls engineer at Mainspring Energy in California. With that being said, I'm just handing it over to Dr. Nilay for today's webinar on the topic orbital stabilization of underactuated robotic systems.
Can you hear me well enough and can you see my screen?
It's little better than the previous one. If you can talk a little loud, that would be much better.
Better now? Can you hear me?
It's still low.
Okay. This is
now it's better. Now it is better.
Okay. Good. Basically I'm using the laptop's microphone now, and I brought the laptop closer to me. Hopefully that would help. All right.
Okay.
So let me get started. You can see my screen though, right?
Yes, I can.
Okay. All right. So thank you, everyone. My name is Nilay Kant, and as Sohail said, I completed my undergrad from IIT Delhi, and immediately after that, I went to Michigan State University, where I did my PhD in mechanical engineering, and Sohail was my batchmate in another department, so that's how I know him. I'm going to present on one of the topics that was a part of my PhD research. And the topic of the presentation is orbital stabilization of underactuated robotic systems. So before I go, into the details, this is just the outline of the presentation today. So within orbital stabilization, we would be talking about two different kinds of strategies that I explored. The first was, energy-based orbital stabilization, and the second was orbital stabilization using virtual holonomic constraints. So before going into the details, let me give you a little bit of relevance. So you can see two pictures on your screen. So let's say on the left-hand side, you see a person who is standing close to a swimming pool. So let's say you are standing close to a swimming pool facing towards the water, and your friend comes from behind and tries to push you into the water. Now, if you are not aware that your friend is going to do that, you would try to avoid falling, and in this process, you would apply like jerks on the joints of your body so that you can avoid falling. Now, on the right-hand side, let's say there is another situation where you are walking in a dark night, and you're not aware of a big stone that is put on the road. So let's say you collide with that stone. Again, your body would try to avoid falling, and in this process, it would apply, large jerks on the joints so that you do not fall. Now, looking at the two scenarios, we can actually model the two systems using a robot. So on the left-hand side, you see a robot model which is called a Tiptoebot, and Tiptoebot basically means a robot which is standing on the tip of its toe. So it's basically a simplified model for a human standing. And on the right-hand side, you see a 5-linked bipedal robot, and this actually captures the dynamics of a human walking. So for the Tiptoebot, you can see that there are 3 links, and we assume that there is a motor to control the upper body. There is a motor that controls the upper leg, but there is a joint here, but there is no motor. So if you see, this has 3 degrees of freedom, but it has only 2 control inputs or control actuators. And why we have only 2 actuators? So if you look at a human being, and if you see the feet, how it interacts with the ground, there is no muscle. So you do not have an active control over the the toe joint. And what you do is using your muscles, the remaining muscles of your body, you control the overall joint. So this is an example of an underactuated system. Underactuated means you have more degrees of freedom, but less actuators. On the right-hand side, again, you have 4 motors, but 5 degrees of freedom, and there is no actuation at this particular joint. So you can imagine that underactuated systems would be hard to control, and hard to control because there are more degrees of freedom and less number of actuators. And also things become more complex because the dynamics is non-linear. So for the example of a human standing or a Tiptoebot being stationary, it means that there is an equilibrium configuration. So if you see the upright equilibrium configuration of the Tiptoebot, it will, and if you design a feedback controller to stabilize that equilibrium will have a region of attraction. So which means that if the states of the Tiptoebot lie within this region, it would converge to the equilibrium. Whereas for a biped robot, it's not a stationary configuration. It's a repetitive motion that we want to stabilize. So such motions are represented by an orbit. And similar to an equilibrium point, an orbit will have a region of attraction, which means that if you start within this region, you have a tendency to converge to this repetitive trajectory. So these are some of the examples. On the left again, orbit can represent a human walking gait, and an orbit can also represent a gymnast motion. For example, if you have seen gymnasts, they can swing their body and they can turn upside down. So there is a repetitive trajectory that they try to achieve, and you can represent that using orbits. So in this particular work, we present a control strategy for orbital stabilization of underactuated systems, and we specifically use a combination of continuous and impulsive inputs. So let's see what impulsive inputs are. So if I throw a ball on a rigid ground, the ball has a tendency to collide and bounce back. Now, if you closely analyze the interaction of the ball with the ground, you'll see that when the ball makes contact with the ground, it immediately changes its velocity, but there is no change in position. And this is because a very large force acts during the time of collision. So similarly, if you apply impulsive inputs on an underactuated system using motors or actuators, the joints velocity would jump, but their position would not change. So that is what we are trying to see over here. So the equation of motion of an underactuated system can be represented in a simple form by this equation over here. And you can please note that here the control input is U, but the control input is 0 for Q2, which means that Q1 is actively controlled using control input U, but there is no control input to actively control Q2. So let's see what happens if U is impulsive in nature. So what we do is we integrate this equation on both sides for a very short interval of time. So the integral of U is the impulse of the force, right? And you can basically ignore these terms because they do not change in a very short interval of time. So what happens is when you apply an impulsive input, there will be jumps in velocity, and these jumps in velocities are given by delta Q1 dot and delta Q2 dot, which is basically the jump in velocity of the active degree of freedom and jump in velocity of the passive degree of freedom. Now, when you apply impulsive inputs using actuators on an underactuated system, The jump in passive velocity is dependent on the jump in the active velocity. And this relationship is given by the impulse manifold. And this is the expression for the impulse manifold. So again, to summarize, if the active joint velocity jump from q1 dot minus to q1 dot plus, the passive joint velocity would also jump, and they are related by this equation. So the takeaway is, if you apply ideal impulsive inputs, it would cause jumps in velocity, but there would be no change in position coordinates. Now, with this background, we are ready to state our formal problem statement. So if you remember the gymnast problem, we are actually trying to, stabilize the orbit for that gymnast. So that's what we're trying to quantify here mathematically. So we assume that, we have an underactuated system with single passive degree of freedom. So if there are n degrees of freedom, there are n minus 1 actively controlled joints and 1 passively controlled joint. And again, the generalized coordinates are denoted by Q1 and Q2, where Q1 is active and Q2 is passive. So the control objective is to stabilize the orbit defined by this equation. And you can see that what we want is, we want Q1 to go to 0, Q1 dot to go to 0, and E to converge to E desired, which basically means that if you consider the gymnast problem, the body of the gymnast would remain, stationary with respect to each other, but the entire body would oscillate at some desired energy. That's what we're trying to achieve here. So the total mechanical energy of an underactuated system can be given by this expression, where the first term is the kinetic energy and the second term is the potential energy, and M is the mass matrix of the system. So the Euler-Lagrange equation, as we saw earlier, can be expressed in this form, where the matrices B and A are given here. So no need to go into the details, but if you get an higher level overview, that would be good enough to understand. One thing to note here is this matrix B is positive definite. So we'll be using this pretty soon. So recall that whenever we apply impulsive input, there is jump in active and passive velocity. But let me ask you this question: what happens to the energy of the system when we apply an impulsive input? And without going into the proof, you can show that whenever you apply, an impulsive input, the change in energy, the overall energy of the system, is given by this expression. Now, one thing to note is, energy is comprised of kinetic energy and potential energy. And potential energy is only a function of position. So whenever you apply impulsive input, in that short duration, the potential energy does not change. The only thing that changes is the kinetic energy. And this is what we have written over here. So in this particular work, we are looking into a very special kind of impulsive input, which is called impulsive braking input. So what we do is, we always break the active joint, which means that after the impulse is imparted, the active joint velocity should go to 0, which means that in this particular expression, Q1 dot plus would be 0. Now, if you substitute Q1 dot plus to be 0 over here, you are left with this term, right? And if you recall, B is positive definite, which means that this entire term is negative. So what this means is, whenever you apply an impulsive braking input, the overall energy of the system is lost. So we always lose energy whenever we apply impulsive braking. Now, let us get back to our problem statement. So if you recall, we wanted Q1 to go to 0, Q1 dot to go to 0, and E to converge to E desired. Now let us construct a scalar function given by this expression. And note that this matrix Kp and Kd is positive definite, and the scalar K is positive. So this means that this entire term is positive definite. Now it means that this will always be whatever you substitute here, this quantity will either be always positive, or it will be 0 only when Q1 is 0, Q1 dot is 0, and E is equal to E desired. So in other words, if we can somehow take the value of this function to 0, we have achieved our goal, right? So let's see what happens when we apply an impulsive braking and what happens to this function. And you can show that if you choose this quantity to be positive, and if you apply an impulsive braking input, this quantity will always have a negative charge. So you can always cause a decrease in this function's value when you apply an impulsive braking input. So now this is the main idea of this work. So we are trying to combine continuous time inputs as well as impulsive inputs. So what we intend to do is we want to design a continuous controller that can reduce V with time. In other words, V dot should be 0 or less than 0. But this cannot be always achieved because we have an underactuated system. So you can specify that V can reduce with time, but not always. So there will be a time when V will start to increase, and right at that moment, we want to apply an impulsive brake. So V reduces, and then we apply an impulsive braking input that causes a negative jump in this function. And then we again switch back to the continuous controller, hoping that it would reduce V again. And the idea is that if we combine these two inputs, we can always cause a monotonic decrease in V, and eventually we would converge to, V equal to 0, which means we have converged to our orbit. So the question is such an approach feasible? And the answer is yes. But we need to answer two things. The first question is, what is my continuous controller? And the second question is, when do we apply the brakes? So we use extensive results from this particular book. And it should be noted that now we don't have a continuous system. We have a hybrid system. We have a continuous dynamics, and then we have the jump dynamics. And we say that, whenever we are not in the set Z, our dynamics is continuous, but when we are in a set Z, we apply impulsive inputs. And we need to figure out what the Z is. So this is the main result of this work. And it says that if you choose your continuous control input to be this, where matrices Kp, Kd, Kc, are positive definite matrices, and if you choose your set Z to be this, you are guaranteed to converge to this orbit. So it means that you have asymptotically stabilized this orbit. And the gains Kp, Kd, and Ke must satisfy some conditions, but they are not restrictive. So the proof of this is a bit detailed. So instead of going into the proof, I have written down a sketch of the proof, the steps that we use. So what we do is we take this Lyapunov-like function, or the function V, and we take its time derivative, and we use passivity. So passivity is that the energy of the system cannot increase unless you apply a control input. So this basically says that the power that is input to the system is only due to control input. So if you take the time derivative of this and use passivity, you are left with this equation. And this is our control input. So we have to choose this U in such a way that we cancel all this nonlinearity here and make this V dot to be negative semi-definite. So this is how we choose U. And once you choose U to be in this fashion, you result in V dot to be this expression. And without going into the details, you can choose your Z to be the acceleration over here. That's the Z is basically this acceleration of the active joint. And then we finally use the invariance theorem to prove convergence. So, if you remember the gymnast problem, you can model this gymnast as a trailing robot with 2 active degrees of freedom, which means that a gymnast can use his shoulder joints or his hip joints to, add energy to the system, but he really doesn't have any control authority. So that's why this joint is passive. And if you look at the simulation results, you can see that the joint velocities, they have a discrete jump because of the impulsive braking. And you can see that the energy of the system converges to E desired. And this was our desired orbit, and you can see that we very rapidly converged to desired orbit by using a combination of continuous and impulsive angles. And if you see here, this is our function g, and you can see it decays to 0, and the joint trajectories slowly reach upright equilibrium configuration. And what we do is, when the gymnast almost reaches the upright configuration, we use a local controller to stabilize it. So that's why you see these states to be stationary eventually. Let me show you an experiment that we did on a rotary pendulum. So, do you see my screen? Go ahead. Can you confirm?
Yes, we can see it.
Okay. So this is an experiment on rotary pendulum, and yes. So let me pause the video. So this is a rotary pendulum, and there are two links over here. There is an horizontal arm, which is like, you cannot see it clearly there, and then there is a pendulum which is attached to this arm. So this pendulum has no actuation, so there is no motor. It's a free joint. And what you do is, you have just a single motor over here, which can control the motion of the horizontal arm. And using that motion, you have to control the motion of the pendulum. And what we do is, we have an additional brake here to apply the impulsive braking. And we use a combination of motor and brake to stabilize an orbit. And that's what you're going to see here. So you'll be hearing some clicking sound, and those sounds are basically when brakes are applied. Okay, so hopefully that made sense. You can see that by a combination of continuous and impulsive input, we were able to achieve a desired energy.
We are unable to listen to you properly. Like maybe like your voice is like little low now. After the video, this happened.
Okay. Is it better now?
It has gone too low. Like Eldo, do you face the same, or like?
Yeah. Is it better?
It is much better now. Yes. Yes.
Much better. Okay.
Yes.
Okay. So hopefully that video made sense. Yeah, so that was the first orbital stabilization strategy that we explored. So the next strategy is orbital stabilization using virtual holonomic constraints. So again, the motivation is, we want to generate a repetitive trajectory, but unlike the last problem where we, the active joints were stationary, we want that there could be orbits where the active joint also moves along with the passive joints. So those are the orbits that we are going to look at in this work. And one thing to note is that this, virtual holonomic constraints could be used for motion planning. So, and the advantage is, we do not have a timestamp trajectory when we use this methodology. So don't worry if you don't know all the details. We'll be getting to that pretty soon. So again, the system dynamics, or the equation of motion, is expressed in this form, where Q1 is the active degree of freedom and Q2 is the passive degree of freedom. One thing to remember is Q2 is scalar, which means that we have a single passive degree of freedom here. So this is my virtual holonomic constraint, and which basically says that Q1 is some function phi of Q2. So this basically means that we always want the active joint position to be some function of passive joint position, right? And it could be as simple as Q1 is equal to minus Q2. So if you have a two link pendulum, if this angle is, let's say, 45 degrees, this angle would be minus 45 degree, and it would always maintain that, constraint. So that's simply virtual holonomic constraint. Now, what we call as a constraint manifold is when we have satisfied this constraint, or when we always satisfy this constraint, we are on a constraint manifold, which means that Q1 is equal to phi of Q2, and derivative of Q1 is equal to the derivative of this term, right? So if you write the dynamics of rho of Q, you double differentiate that expression, and this is what you get. And what we want is, we want rho to be 0. And if rho is 0, it means that Q1 is equal to phi of Q2, and that's what we want to do. So if you write the double derivative of this, you get this expression. And what we're trying to do is, we are trying to feedback linearize the system. So we choose U so that we cancel all these non-linearities, and then, and then come up with a PD control that can stabilize this. So we choose the gains Kp and Kd such that the residual dynamics is given by this expression. And you can see that if Kd and Kp are positive, rho will converge to 0. Okay, so now since we can stabilize, our constraint manifold, we have utilized all our control inputs, right? But then there is a passive dynamics. There is a passive degree of freedom which still is not controlled, and we want to see what happens if we substitute this control input. So when you do that, the passive dynamics can be given by this expression where Q2 double dot is alpha 1 plus alpha 2 Q2 dot square. Now, if you integrate this equation, this has the dynamics, or this resembles the dynamics of a simple pendulum. So if you consider this as a simple pendulum, the mass matrix is like this expression, and the potential energy would be something like this. So which means that this is again an Euler-Lagrange system with some potential energy function. So if you choose different potential energy values, you will get different energy level sets. In other words, there are a wealth of closed orbits for this, residual dynamics or zero dynamics, and those wealth of orbits are characterized by the different potential energies. And there is a theorem which says that these orbits would be stable but not asymptotically stable, which means that if you start on that orbit, you would always remain there. But if there is some perturbation, you would drift away. So there is no tendency for the trajectories to converge back to the orbit. So what we want to do is, we want to select a particular orbit and then also asymptotically stabilize it. And let's call our desired orbit as OD. Now, for this, we construct a Poincaré map. And to understand Poincaré map, let us look at this diagram. So I want you to ignore these, these black lines over here. Just focus on the red ones. So this is a repetitive trajectory in state space, right? So this theorem says that if we are on this orbit, we would continue to trace this orbit. But if we drift away, we would not come back, right? So instead of looking at, this entire orbit, what we do is we construct a section, which we call as a Poincaré section. So we construct a section of this trajectory. So you can imagine that this section would intersect this orbit at a single point. And we call this as the fixed point of this orbit. So if you are on this orbit, you will always, in one period, you would always intersect this point again and again. So now let's say if this point was attractive, right? This means that if you start from away, the intersection point would slowly approach this point, right? So in other words, the stability of this orbit can be investigated by simply looking at the stability of this particular point. So, and some of you would have guessed it right. You can represent this map using a discrete time system. And this is called as a Poincaré map. So what we do is we construct a Poincaré section where, the passive joint angle is constant, and the Poincaré map is given by this expression. So one thing to note is, since we have fixed Q2 over here, we have one state less. We have n-1 states of the Poincaré section, and we denote this by Z. Now, if you substitute Z star, which is the fixed point of this map, you will return back to Z star. So this map will, will say that if you start from Z star, you'll reach back to Z star. And that's the fixed point. Now, if you linearize this map about the fixed point and compute the error between where you are versus the fixed point, you get this particular expression where E is, the error between Z and Z star. And the stability of this map, as we saw, that can be, investigated by looking at the stability of this discrete system. And since we know that these orbits are not asymptotically stable, the eigenvalues of this matrix would not lie within the unit circle, right? So we need some mechanism to, push the eigenvalues within the unit circle. And what we use is we leverage impulsive inputs. So what we do is we say that whenever we are on the Poincaré section, whenever we are crossing the Poincaré section, we'll apply an impulsive input, and that would drift the trajectory. And then maybe in the next intersection, we would come closer to the fixed point. So that is what we're trying to do. So our control input is the impulse I that, this impulsive input imparts to the system. So now if you look at this Poincaré map with this new input Ik, this is how you can represent the system. And what we do is we linearize this map about the fixed point and about, the nominal impulsive input, and you get a linear discrete time system. And these matrices can be computed numerically. So this is the main result. It says that if the pair AB is stabilizable, the orbit OD can be stabilized using, discrete impulsive feedback given by this expression. And what we are trying to do is, let's say you start from a point 1 and the trajectory intersect this Poincaré section at point 2, right? So this is not Z star, and we would never reach Z star because we need to do something. So what we do is we apply an impulsive input. This moves the state of the system on this Poincaré section, and then we rely on the continuous controller. We don't do anything until the next intersection. And at the next intersection, this point is now closer to Z star. And if we repeat this process, we will eventually converge to Z star. So this is an example of, the 3-link robot that we saw. This is our desired orbit. And you can see that using this combination of continuous and impulsive inputs, we converge to the constrained manifold, you can see here. And this is the error on the Poincaré, error between the state and the fixed point on the Poincaré section. And you can see that with cycles, we converge to equal to 0, which means that we have converged to our orbit. So this brings us to the end of our presentation. So let's see what we saw today. We saw a general result for orbital stabilization for a class of systems. And to note is, like, in regards to previous works where, people look at one system and analyze the stability and design controllers separately, we presented a generalized methodology which can, target a class of underactuated system. The generality of the method was shown using simulations on 3D of system as well as experiments. Some new results were presented, such as, impulsive braking causes negative jump in, energy of the system and Lyapunov-like function. And finally, we saw that stabilization of the desired repetitive motion can be achieved using the VHC approach, where we again use a combination of continuous and impulsive inputs. These are some of the publications for this work as well as some of the other works that we did in regards to impulsive inputs. And yeah, thank you so much for listening, and I would be happy to answer any questions you have.
Thank you. Thank you. It was a wonderful presentation. It's far away from my expertise, but I'm still like really curious of the work that you have done. In fact, I never seen those experiments like the pendulum work that you have done. I'm just curious, like, so you said like you developed this particular control system and you implemented that system into the pendulum.
Yes, that's correct.
Okay. So you said like you applied a braking, right? Like once it reaches on the top of it.
Not on the top of it. So the braking is applied intermittently. So we have the motors are applying torques continuously, right?
Okay.
And intermittently, based on a control logic, we break the joints, right? And that's based on a condition. And what it does, that the combination of the continuous inputs that we apply and the braking, we converge to the desired energy level set. Does that make sense to you?
Got you. Okay, that makes sense. So now you're telling like there is this Poincaré map, and it has been told that once it is outside its trajectory, then it is difficult to bring it back to its original orbit. And you use the other methodology to bring it back.
Right.
Okay, so now even if you go outside the trajectory, now your system can take it back. Okay.
Converge. Yeah. So just to give an analogy is that, if you have, a biped robot, right, which is tracking a repetitive trajectory, and then there is some perturbation, some uncertainty, like there is an obstacle which it encounters, right? The controller can have the tendency to, track that trajectory despite those uncertainties. Does that make sense?
Yes. Yes.
Yeah.
Got it. Yep. So there is one person who asked, what is V, the capital V, like you said, like there is a scalar constant.
Okay.
And he's just wondering, what is that?
Okay. So V is basically, I don't know if there are people from controls background, but V is basically a Lyapunov function. So let me give you the intuition behind this. It's like a energy function of this particular problem. So if you see this function is comprised of three terms, right? It's Q1 transpose KP Q1, Q1 dot transpose KT Q1 dot, and KE minus E desired whole square. So if you remember, our control objective was take Q1 to 0, Q1 dot to 0, and E to E desired. So if I substitute Q1 0, Q1 dot 0, and E equal to E desired, this entire term becomes 0, right? But this term is always positive. So no matter what you put here, this term will always be positive unless you are on the desired orbit. So it's a way to quantify our problem. So the thing is, if we are able to take the value of this function to 0, it means that we have achieved our goal, right? And that's what we're trying to do. We are trying to design controllers so that as time passes by, the value of this function decreases and becomes 0 eventually. Does that answer the question?
Yes, that answers the question. In fact, there is another person, Abdullah Al-Ahdal. He is asking, like, can you please share your emails so that we can contact you? Only if you're okay with that.
Oh, sure. Yeah. Okay, I can now see the questions here. Okay. Speech. Okay. Yes. So I don't know if there is a chat box, Sohail.
Yes,
but
there is a chat box.
Okay, I don't. For some reason, I cannot see it.
Or I can share it like later.
Yeah, you can share my email.
Yes.
I'm perfectly fine with it, and I'd be happy to answer any further questions that come up later. That's fine for me.
Sure, thank you. So like if anybody have a question, please raise your hand so that I can allow you to talk. Okay, there is Sharif Muhammad.
Good morning, Doctor. Thank you so much for your presentation.
Thank you. Thank you, Sharif.
Regarding slide 29, I believe, you
Slide
mentioned,
20.
yes,
Yes.
yes. You mentioned, yeah, this mechanism, yeah. You mentioned linearization around operating point, okay? Z
Right.
star, okay? And to apply this particular mechanism, you mentioned another operating point or another point. I believe point number 4.
No, that's not. I think you didn't understand exactly what I was saying. So we do not have different operating points. We just have one operating point, which is Z star, right?
Not operating
this
point. It is another point. Another point. I think in slide 27, yeah. So you mentioned Z star. This is the operating point, and you mentioned another point for applying this mechanism. So
right. Okay.
Yeah.
Okay. Complete your question. I will answer.
Yeah. This is my question. Can you clarify about the other points to apply this particular mechanism?
Okay. So let me clarify what I said. So we have an orbit, right? And if you construct a section of this orbit, that section will intersect the orbit at a single point, right? So the idea is that we want to converge to this point. So how we do that? What we do is, that let's say you start at a different point, right? And you have a continuous controller. This continuous controller would do whatever it wants to do, but it would not take it back to this, red trajectory. So the trajectories would intersect at some other place on this section, right? And if you don't do anything, you would never converge back to this point. So what we do is we have a discrete controller, right, that applies an impulsive input whenever you intersect this section. And we show that this discrete controller has a tendency to bring this point towards this point, right? But it would not do it immediately. So what you do is we shift the point, because when you apply impulsive input, there is a discontinuous change in the velocity, right? So what happens is when you apply an impulsive input at point number 2, the trajectory jumps to point number 3. And then you switch back to your continuous controller, and this continuous controller, and you wait. So what happens is this trajectory again intersects this section at some other point, which is called point 4, right? And if you keep on repeating this process, this intersection point, you will see that it will start to approach this point Z star. And this is what we're trying to do here. Does that answer your question? There is no operating point other than Z star. It's just, this diagram is just showing that there are several intersection points that would happen with time, and eventually these intersection points would converge to Z star.
So from point number 1, it will approach to or it will go to point number 2, then point number 2 to point number 3, then from 3 to 4,
right.
And point 4 will approach on the plane to Z star.
No, so this is one cycle, right? I've shown you one cycle or 2 cycles basically, but with when the number of cycles grow large, you'll see that this point would start to approach Z star, right? This is just
on the plane.
Sorry, what? Come again?
It will approach on this particular plane or an other plane.
On this particular plane, right? Yes.
Okay.
And when it approaches this on this particular plane, when you reach Z star eventually, then you will stay on this orbit, right? Because you have a controller to maintain you on this orbit, but you don't have a controller to bring you to this orbit. And that's what the impulsive controller is doing.
Yes. I'm sorry, Dr. Sir. Another question. If
No
Sure,
you
sure,
problem. Go
sure.
ahead. Go
excuse
ahead.
me. I am sorry I came late, but you explained PID controller for the inverted pendulum at the beginning of this presentation.
It was not a PID controller. It was a nonlinear controller. Yeah.
Yeah. So can you talk briefly about it? What I saw KB, KI, KD, right?
Uh, let me go back to the slide. Yes, this was the controller that is used. So what was your question, Sheriff? I did not get your question.
Yeah, you mentioned the controller gain matrices KB, KD, KE. It is non-linear controller, but specifically, what is the name of this controller?
I don't have a name for this controller, but this is, yeah, I don't have a name for this controller. This is just a controller that we designed. You can call it whatever you want.
Maybe place control.
But
Okay.
yeah, remember one thing, that this is a hybrid controller. So this is the continuous part. And then we have an impulsive braking part, which happens whenever you are in this set C. Right? And it's a combination of these two inputs that guarantee convergence to the orbit.
Yeah. And the Lyapunov function for stability.
Yes, we use the Lyapunov function to prove stability. That's correct.
Yeah.
And not only that, our controller is designed to, you know, like our controller is designed to let V converge to 0. It's like a control Lyapunov function.
Yes. Thank you so much, Doctor, and very nice presentation.
Thank you. Thank you so much.
Thank you, Dr. Sohail.
Thank you.
Yeah, so as Sharif was talking, Nilay, like this is one of the best control presentation that I have sat into. Because I always found it like extremely difficult to understand most of the thing, especially like if you don't connect it to the practical applications, it's quite difficult to understand what you're trying to do.
Right. I think I have been into that situation, and I run into that situation because still I don't understand everything that people talk about. So yeah, that was the motivation that I should give a talk, so that at least it is, you know, people can understand it on a higher level, and hopefully
perfect. This is one of the best, I would say, like which I have attended. So
thank you.
Guys, if anybody else have a question, please feel free. Like Dr. Nilay will be there for like until 10:30. Like you have like 5-7 more minutes. If anybody have a question, please raise your hand so that I can allow you to talk. Okay, so it looks like we don't have any more questions.
Mm-hmm.
So
yes, and I'm happy to answer any follow-up questions, you know, via email.
Thank you, Nilay. Like it's much appreciated. Like no, we are really thankful for your time.
Thank you.
And
sure.
it's like we pulled you in your work time, or like it is outside your work time.
Well, this is actually night time.
Okay.
It's 12:30 a.m. I think right now.
Thank you very much for this
fine.
time. Like we really
no
killed your
worries,
sleep.
No. Sorry, Suhail, I couldn't hear you.
We killed your sleep. It looks like that.
No. I generally sleep around this time, so
okay.
That was okay.
Thank you. Thank you. Much appreciated, Nilay. And then we'll talk later. Then, like if anybody have a question, then you're okay to answer it by email, right?
Yeah, absolutely.
Thank you. Much appreciated. And
all right.
Thank you for your time.
Okay. All right. Thank you, Sohail, for the invitation. Really thankful to the university for, you know, giving me this opportunity. And yeah, we'll connect on
definitely. And this is a recorded session as well. So anybody in the future, they can listen to your presentation. Thank you.
Absolutely. Okay, that's nice. Can I get a link to this recording if possible?
Definitely, we'll send you the link. In the future.
Awesome. Awesome. Okay. Okay. All right. Thank you, everyone. It was great to talk to you.
Thank you.
See you later, hopefully in the future.
Yes. See you.
Thank you so much, Dr. Nick.
Thank you. Thank you. Bye.